So here we have Giuseppe Broccolo, and he's going to talk about data science with Python. I hope you enjoy it.
Hello? Can you hear me? OK. So yeah, I'm Giuseppe, data engineer in Decibel. I work mostly designing data pipelines. Just to introduce the topic of the talk, let me quickly introduce one of the most efficient pipelines present in nature. Is the enrollment of a DNHA. It's one of the most efficient process from data pipelining point of view. But if you consider the speed of the enzyme involved in this process, the process will take 20 years. So the secret is that actually the process scales. So actually it takes 20 minutes. So this is a link to the repo presented in this talk. So I invite you to have a look directly to the code if you can. Also because generally my code skills are better than my presentation skill. So if you can, please do it. So this is the outline of the talk. Essentially, I will present the requirements needed to deploy a good service in scale. I will present a simple prototype that need to be deployed as a service in scale. I will present the roadmap, so all the steps needed for this, focusing, of course, on all the changes needed from Python point of view, and then just conclusions. So there is a document. It's called the 12-factor document. It's essentially a document prepared by Roku guys, where they explain in 12 steps how to essentially deploy a successful service in scale. I'm just summarizing here some points. So essentially just to present the situation, or essentially a good application that works in scale should be a stateless application. It should work asynchronously. This is generally actually something that is good always, not just to work in scale. Should ingest input data as more as possible, not like files, but more HTTP requests. Even better if consuming a streaming like Kafka streaming and so on. We should avoid any persistence in file system. For example, configuration should be passed as environment variable, for example. Also, temporary artifacts, we should avoid them as more as possible, prefer in-memory execution. In case this cannot be avoided, okay, rely on some backend services like, I don't know, some caching service, DB, cloud bucket, and so on. Of course, one of the most important points is the portability and the easy deployment of the processing units. So Docker here is a fundamental technology for this. So the scenario. Essentially, let's consider a case when data science team has found a fantastic algorithm just to detect, for example, the anomaly of a Gaussian time series. The idea is to transform this in a responsive in-scale service that ingests the time series via HTTP request. I'm reporting here just an example, for example, of HTTP request for this, where the time series is provided in the body of the request itself. This is an example of code. It's really simple. I mean, it's just a simple function that relies on a moving window, essentially where it compute the average of the time series and essentially detect the anomalies through the computation of the standard deviation. Just NumPy and the pandas are used as dependencies. So now we'll present the roadmap. As promised in the abstract of the talk, 5 steps. The first step is to define an importable module, so transform the Jupyter notebook, for example, of the prototype. Consider if Jupyter has the environment where the prototype has been developed in an importable Python module. So the idea is to create a package. So as you know, so define some init file where to include all the initialization of the package, for example. Put the code as it is in a Python module, maybe checking, of course, the syntax of the code, because generally when we prototype, the code is not always clear, so just taking a bit care of it. Some flake8 check could help. And then use setup tools and to create the module, put all the the dependencies in the requirements file, and you can find all the more details in the link I presented at the beginning, if you want. So the idea is this one: you can easily install import the module, installing with pip. There is no need of the source code. In this way, you can just easily import the modules in. Thank you. The module in your environment, essentially. So the next step is to expose a responsive endpoint. This is actually a well-known pattern in Python in order to create microservices. So essentially using Nginx and UWSGI with Flask to expose the code. There are a lot of references on web, so I will not go in details in this. Just I would like to focus on the Flask application, for example. So here you can see the ingestion of the data. So all is made in memory and is passed to a pandas data frame that can be used for the computation of for the detection, of the anomaly, and passed to our module, essentially. So the third step is to make it asynchronously. Consider that, for example, it can take some time for the processing. So for this, we are using Celery. The idea is to reduce the impact to the requester as more as possible. So in order to avoid just to send a request and wait for the response. So the idea is, OK, as far as I'm able to collect the data, I will send the request, and then I will, in a second moment, I will get the response asynchronously. So for this, OK, the idea is to use Celery. So Celery Worker is essentially a scheduler of asynchronous task. The idea is to rely on a backing service. In this case, we will use Redis for this. The idea is to submit the task into the Redis broker. The Celery Worker is able to get the task, process it, and put the response in Redis itself again for to provide to the client the response, essentially. So this is the change needed in the supervisor. I mentioned before, supervisor is used to handle all the tool used inside the Python microservices. Here, there is the configuration of Nginx, UWSGI, and I added here the configuration of the Celery Worker. Here is the change in the Flask application. So we have to configure the Celery scheduler, and configuring also the Redis cache for as backing service. I use Redis as a secondary cache in order to store also the task ID of the submitted task. Sorry for the game. And here is the configuration of the asynchronous wrapper that executes our method, the method that we implemented for the anomaly detection. So here is the change in the endpoint. So the endpoint has to essentially to handle both post and get request. In the post, essentially, it's really similar to the previous one. We ingest the data, and we essentially pass to the Celery wrapper. We have to pay attention that Celery is not able to ingest not a JSON serializable input. This means that we cannot pass the pandas data frame as input. We have to serialize it into a JSON. So this is done with 2JSON function, for example, here in pandas. And that's all. So from the get point of view, the get has to just read the get. Thank you. has to read the Redis cache in order to check if the asynchronous task have ended, have finished. So checking also the status of the task, and returning eventually the output in the case it concluded successfully. Of course, he has to handle all the secondary cache where the task ID are essentially stored. So the idea is to check for first the oldest task submitted, essentially. Okay. Of course, is needed a change also from in our module, because now we are passing a serialized input. So the idea is that, okay, data scientists were thinking to work with pandas data frame, so just give them back a pandas data frame as well. So the idea is to deserialize the input that is received in this way. Okay, so the first step is to use Docker. Do you know Docker? How many of you knows Docker? Okay, a lot of people, fantastic. So it's a wonderful tool, essentially, yeah. So the idea is to Dockerize our service into 2 containers. I will explain why a dedicated container for the backing cache, and of course, define the container of our main application that include all the Nginx and all the Python code and the Flask application and Celery as well. This is the Docker file. Essentially, I'm starting from an image that we have released, is public, you can use if you want. It's essentially an image that already contain Nginx UWSGI installed, Flask essentially, and all and pandas installed in an Alpine environment. So essentially, once we have this image prepared, of course, this image is inherited from an already existing image, this one. And the idea is to, of course, put our code and put the Flask application here. Just use pip to install the module, and that's all, essentially. Okay. If you want to test your Dockerized application, you can. Just use Docker Compose for this. This is the configuration of the Docker Compose to test it. Essentially, it deploys to services. So our main application, exposing port 80 for HTTP request, and the backend service based on Redis. So the idea is to part of course, the Redis cache is configured through an environment variable, as I was mentioning at the beginning. Consider the 12-factor document, and inside Docker, okay, the idea is to create a Docker network, and within the Docker network, the container is just resolved through the name of the services you give, essentially. So once you deploy it, essentially you have a service ready to serve listening to port 80, essentially, where you can submit the HTTP request I presented in one of the first slides. So the last step, when you have verified that Dockerized service work, is to, okay, just start the deploy in cloud, for example, using Kubernetes. So this is the engine that will be used to create our service in scale. So how many of you know Kubernetes? Okay, a good number, okay. So what is Kubernetes? There is a lot to say about it. Probably I have to study a lot to know it very well, but just to give you some input, it's a way essentially to create a dynamic cluster in terms of worker units. So the idea, you can define a cluster that can auto-scale horizontally in order to provide the processing unit ready to ingest your data, your request, and so on, essentially. There are several cloud providers that provide the Kubernetes, 5 minutes, that provide Kubernetes as a service in Google, in Amazon, and so on. So this is really good because in cloud it's really simple to just add workers, also physical workers, to the Kubernetes cluster in order to scale and to deploy further processing units. So just to give some introduction to Kubernetes resources, I'm listing here one of the most important, not the only one, but one of the most important elements in Kubernetes. The most important part is the pod, the so-called pod, that is the processing unit itself. Essentially, is an elementary unit that includes one or more containers, essentially the whole service, that for example, the 2 containers that we defined before with the Docker Compose, for example. Then you have the deployment. The deployment defines how the pod are deployed in the cluster. Then you have to define a service, so how the deployed pod are exposed to the rest of the world, so how the requests are ingested and so on. So you can find a full example in the link I presented at the beginning of the talk. And then you can define the so-called horizontal autoscaler, so you define how the processing unit really scale based on the request they receive. So here there is, without entering too much into details, so this is, for example, the configuration of the processing units of the pod. The idea, you can define, it's really similar, the configuration to the Docker Compose one. So you define essentially the 2 containers that will deploy the service, essentially. The idea is to, the image, generally in cloud, you don't build the image, you just put the image in some registry in the cloud itself. So you can put the already built image. You pass, essentially, you are able to resolve the Redis cache just as a localhost, because inside a pod, all the containers are defined as localhost requests. And you can also define a limitation about the amount of resources that a pod can use, both in terms of memory, for example, or CPU, like listed here. In this approach, there is a problem, because, just deploying a single unit where the backing service and the processing unit are together in a single pod can be fine in a static case, but in case of a scalable cluster, this is a problem, because generally pods are destroyed as far as they are not used anymore. Could be that you weren't able to get the asynchronous response in the meantime, so this means that your process has been lost, essentially. So the problem is that the cache in this case is volatile. To avoid this, you have to decouple, essentially, the processing unit and the Redis cache into 2 distinct services, actually. So in this way, the Redis cache is persisted. The idea, you can define the so-called cluster IP service in Kubernetes. That is, it's a particular kind of service that accepts requests just within the cluster itself. And this is the change of the configuration of the pod of the processing unit. In this case, you have to change how the Redis cache is resolved. So in this case, it's resolved with the name of the service deployed in Kubernetes for the Redis cache. So essentially, I presented all the 5 steps here. There are room for improvements, for sure. This is just a stupid example, but just to explain how to play a bit with Python in order to achieve this kind of services. As I mentioned before, the best would be to consume streams and publish in stream as well, the output. Important, we should make the backing service, so all the Redis cache more reliable. This means not just creating a single Redis container for it, just creating a cluster for some HA. And of course, one important thing also will be to decouple actually all the part of the celery worker from the ingestion of data and make scale just this part actually, because this is the part that needs to be scaled, essentially. Good, so I concluded, exactly, perfect. So I concluded. This is just a summary of the step we made together. Question?
So does anybody have any questions? Nothing? One there. Good.
It's more of a comment, really, and thanks for the detailed talk, by the way. I will phrase it as a question. I didn't realize we were being very strict in that format. I apologize. Okay, have you heard of ASCII, the asynchronous version of Whiskey, essentially? And would that be more useful in this context than Whiskey, particularly if you want to stream the HTTP response? Obviously, you wouldn't then separate out the
I think you need to put the microphone closer.
Yeah, no, I didn't understand the question, sorry. Yeah.
Have you heard of ASCII, A-S-G-I? There was a talk about it.
Yeah, there was a talk before. Yeah, unfortunately, I wasn't there. I didn't know it before. Probably I will have a look for sure to it. Yeah. Yes. I don't know. One thing that I like of Celery is that, of course, here I presented a case where the Celery worker was deployed locally with the Flask application and all the rest of the code within a single processing unit. But the idea is also to create a cluster of workers. So this is something that I like because it's really easy to deploy and it's really... So I will study for sure. I didn't know that that kind of framework. So if it allows something like that, perfect. I have found an alternative to what I was knowing. I was citing Celery here before because it's just well known in the Python, of course. But thank you for, thank you.
Any more questions? Anybody? No? Then. Anybody? No? Okay. Then thank you, Giuseppe, for the talk.
Thank you.